This is video 3 out of 4 for class 3. In this video, we'll talk about data lakes and the ELT pattern, which is the counterpart to the ETL pattern we've seen previously. So recall that some people have said that there are issues with data warehouses, data marts, in the traditional ETL pattern, namely that they lack agility and flexibility because there's a lot of rework involved. They're usually required that we know ahead of time what we will do with the data and what the data structure needs to be, and it is stored in a relational database where we need to maintain a schema and a structure and so on and so forth. So what it means is essentially it's considered to be a bit too heavyweight for the agility that businesses require nowadays as competition moves faster and we're trying to have decisions made faster than ever before through the use and the analysis of increasing volumes of data. Now, for a long time, there was no better alternative. Essentially, all we had was our ability to build relational databases, and innovation through the data warehouse industry was primarily based on incremental innovation. There were a few things that were improved. We found new patterns to store data and process it based on certain needs, but there was no radical change that was taking place ever since it was offered in the late or in the early 1980s. So most of the innovation was incremental, and we sort of hit a roadblock when suddenly we were facing with vast quantities of data coming in a variety of formats and at very high speed or high velocity. So the emergence of distributed storage and computing frameworks, remember when we talked about Hadoop, for example, has brought innovation for this domain in a way that we did not envision back then, and really has allowed us to open really a lot of the technological, but some of the analytical and managerial aspects of how we use to analyze data. One of the ways through which this is done nowadays is with what we call a data lake. So the idea behind the data lake was originally offered by the CEO of Pentaho in 2010, although it was not really fully implemented until a couple of years later in the majority of the industry, but it's a very simple idea. The idea is to ingest data from many places and in many formats. And with our distributed storage systems, we have the ability to do so. We want to keep the data in raw or near raw format in one centralized repository, a little bit like a data warehouse. We're still having separation of concerns because the operational data will not be connected to our analysis pipelines. Rather, the operational data will be fed into our central repository, but once that feeding has been done, there's essentially no connection between the two. The other thing which is crucial is that rather than transforming the data prior to loading it into its final destination so that it fits a predefined data structure that we've created for this purpose, we will let the people who need to analyze the data perform the transformation themselves. So what we mean is that we expect that data analysts, data scientists, and data engineers can dive in and swim for the data and retrieve it that way. And what this opens is really the ability to do self-service data analytics. If you have a central repository of data, you're able to get the data you want, process it the way you want, transform it any way, and manipulate it any way you wish, and then run the analysis you would like. All this in the name of increased agility for the extraction of value from data. And it makes a lot of sense if you think about exploration again, because exploration requires you to find new ways of performing existing processes. So if we talk about data analysis, artificial intelligence, analytics, you need to be able to manipulate data in a various number of ways before you find the ones that bring you the innovation you're looking for. And that means trying several things. If you have to modify a data warehouse every time you want to do this, you do not get the speed and the degree of agility that you need to react fast in a fast-changing market such as the ones we're in right now. So in terms of architecture, there's really two main requirements. The first one is we need scalability. We need a place where data can grow at scale, and this is why we rely on something that provides horizontal scaling. Not so much increasing space and memory in a machine, but adding machines that can work together. The other thing we need is compute functionality. Why do we want to have the two is because if we say that we have a place where we store tons of data, but users have to download this data to process it or move it to another place where they can process it, it's going to be very long and not very flexible because it will always be time consuming and require taking data, downloading it, sending it to another place before it can be processed and removing it from the destination once the analysis is performed and so on. And it's not very flexible and it doesn't help. So what we want is a place where we have both storage and compute functionality so that we can send commands to get the data and process it at the same time. In the early 2010s, the default candidate for this was Hadoop. Why? Because it takes care of the storage, but it also takes care of the parallel programming framework that allows us to do some computing as well. So we've said in the past that there's a variety of components that are involved in big data solutions. We've talked about how we need to do ingestion, we need to do processing, analysis, generation of output, and so on. And we had said that part of these processes are handled by different components. So what we find here is that there's a variety of components involved and that many of those are open source projects or derivatives of open source projects. At a high level, Data Lake will include functionality for ingestion. Retrieving the data from operations could be by being connected to our operational applications and systems and listening to changes so that we can bring those changes to our data lake, or it could be by retrieving the data in real time or even in batch if needed. And you'll find products in the open source world such as Kafka, Flume, and Scoop that will help you do that, but there's a number of other ones as well. In storage and batch compute, you will have products such as Hadoop, Hive, HBase, and essentially here the idea is you ingest the data and now you need to store it and you need to compute it on a batch basis because you have to perform, for example, daily operations, daily number crunching to prepare some data for data analysts. If you need faster computing, you can move to real-time compute with other products such as Samza, Spark, or Kinesis that allow you to have really the ability to react in real time. So your data lake might be ingesting data in real time, storing it in near real time, and reacting very quickly so that you can refresh analysis not every day, but 2 or 3 times a day or every hour, even if you have the right pipelines defined and the ability to do so at a large scale. So some of the pitfalls we see with data lakes are primarily non-technical. That might sound surprising given the complexity of these infrastructures, but most of the issues we have that result from their implementation are not technical. They're managerial and they have implications not for the technology, but for the creation of value for the organization. The number one pitfall is the creation of data swamps or data dumps. Essentially, it's this idea that when we talk about ingesting data into a centralized repository, there's this reflex of trying to ingest everything. The data will land in a place, but it will never be used. It is very costly to do, and it's costly to maintain, and it also doesn't serve any purpose. The number two pitfall is if you build it, they will come. So IT function might get assigned to create a data lake and pump data in its raw format. But what we've seen with some of the companies that we've studied in some of the data lakes projects they've had is they realized once they build it and the data lands, people are not able to find their data they want. They have no idea what data is there. They can't assess the degree of reliability of the data. So having a logic of we'll just build it and people will have it and they'll use it is not really working that well. The number three thing that we've seen is letting the data scientists deal with all the mess. The logic of just bringing raw data and have the data scientists spend all this time having to manipulate the data before it is in a working format doesn't really work. So here what we find is that curation of data is a crucial element in data lakes. There might be different zones in a data lake where the data is in various levels of curation. For example, not curated, lightly curated, and highly curated. And at each level, we have different standards of quality, reliability, formatting that is applied, a certain number of missing data that is allowed, and so on and so forth. But the idea here is that a one-size-fits-all raw format data place where we just throw everything in will not work. We need a way to be able to have data that is raw or near raw, but we still need to be able to locate this data and assess its reliability. So throwing all and any data in a data lake, it's inefficient, it's expensive, and it will not contribute to value creation. Another question, if you do that, is, well, can you use data from 15 years ago to make predictions about tomorrow? Maybe, but maybe not. The way Amazon operates now versus how they operated 15 years ago is vastly different. So are you able to use that data from the past to predict the future given the state of your business processes? That is not always the case. So we have to think about which data we actually want to get. When companies set up data lakes, one of their objectives is sometimes to migrate their data from their data warehouses into their data lakes, but it might not make sense to get all this past data. And one of the reasons this data is there in the first place is because the company just does not want to get rid of it. But there's no real logic from a value creation perspective. The idea here is that we need to ask these questions so that we are able to determine what are the real requirements that we have for our data lake and how will we drive the life cycle of the data within it. And we'll talk about data life cycle as an important element when we talk about data governance. So some success factors that we found in projects that are working with data lakes are the fact that you ingest the right data. What we mean by this is that the data should be connected to a business use case, which is connected to the creation of value for the realization of the strategy of the organization. Setting up a central repository for data without any sort of objective as to what this data is supposed to do is not working very well. We also want to have a validation and an audit of data quality in place. Some organizations, as I've said before, provide different levels, such as raw, curated, and reliable. The idea being that it's okay to have raw data, but the type of insight we can derive from it may not be as reliable as the kind of insight we get from the highest level of curation from within the data lake. We also need a way to inventory the data. Imagine if all the systems within your organizations were throwing all their data in one place. If you arrive there, remember the analogy of the data lake where you're supposed to swim for data, you will literally be drowning with data and you'll never make it. You need to be able to find a way through the data, and that means that you need data catalogs, you need data inventories that allow you to locate the right data and perhaps to assess their degree of reliability at the same time. So we need to provide the means to locate and use the data. In other words, we need to help our users of the data lake get the data they want, because otherwise it will end up being a data dump and nothing will happen with it. So one of the questions that people ask when we say these things is, well, but what if later I want to do this and I did not think about it and I was not ingesting this data to begin with? I should just ingest everything just in case later we want to do something. It's a very valid question. But the problem is this logic has pitfalls because you can say that about any type of data within the organization. So one of the ways organizations try to circumvent this issue is to build their data lakes incrementally. So every time you bring data in, it should be to serve a use case to create value. So you associate the incremental growth of your data lake as part of your big data initiative that is built on a series of use cases that you want to achieve. Otherwise, you will spend a considerable amount of time building a data lake, and after a year or two, there will be no value creation whatsoever. It will all have been a huge cost. And this is where you can say, okay, now we can move to create value through analysis, but at this point, you've already ingested so much data that it's going to be hard to determine this is the use case we want to implement to create value. You need to move progressively, and one way to do so is to have your data lake grow with your big data use cases as they're being implemented. So early visions of the data lake as a central repository of knowledge that is just waiting to be tapped in by scientists have proven to be largely overstated. Discipline and knowing the data you need to create value based on a certain use case will drive the value creation process. Having data there for the sake of having data there without a connection to value creation will not help. So When we look at the data lake, we're really changing the paradigm of how we work with the data. If you remember data warehouses, data marts, we've talked about the ETL process, extract, transform, load. Here we're moving into a logic of what we call extract, load, transform. So we load the data into our data lake after extracting it, but we do not transform it. We leave the transformation for afterwards from data specialists. Why? Because based on their needs, they need to transform the data in different manners. Certain types of analysis require certain types of variables. If those variables are already formatted in a certain way, we may not be able to try different types of analysis. And we need to be able to try these types of analysis to figure out which model works best, to figure out where the value creation is maximized, for example. One of the advantages here is that it removes some pressure from IT. Why? Because the IT is there to support the infrastructure, again, as an AI-ready IT function, as we've said before, but it is not in charge of maintaining the actual data in it and the structure in it through a series of transformation processes like they usually do with ETL processes. It's also a fault-tolerant architecture. So data warehouses can be extremely expensive to operate because they're usually single or dual server environments where you're really trying to ensure that there is a maximum service level that is provided and that you minimize the possibility that a fault will occur. When you work with scalable systems, such as horizontal scaling systems such as Hadoop, the system is built with replication built in so that in the event of a failure, a recovery is very likely. It's almost guaranteed unless you have a massive failure of a majority of the computers working in your cluster. But the idea here is that failure is incorporated into the way the system operates so that it can work its way around failure while you maintain it and fix those issues that happen along the way. So some of the pitfalls of the ELT logic is inefficiencies. First of all, if your data analysts are responsible for transformations, well, you might have 20 people doing the same transformations without knowing that they're all doing the same work. Why? Because they all get the same raw data, apply the same transformations. This is where different levels of curation can be useful so that there is a way to have common transformations applied and serve as the basis for the work of people that are more on the edge of the analysis pipeline. You also have a heavy reliance on data specialists. That is often an issue because your business users, which were the targets of your traditional data warehouses, will not really be able to play in your data lake. But if we switch into a logic of being in the age of analytics, you need the people who are professionals and who really know how to work with data and create insight from data, work from your data lake, then that is absolutely fine. It's just a change in how we think about data for the purpose of analysis. You also have often a lack of monitoring and auditing because you have data that sits in raw or near raw format. And when you do so, the transformations can be applied by the data scientists, for example, but they need to be the ones who validate their transformations. There is no central process in place to audit that these transformations are done properly. The other thing you might have is less cumulative knowledge and established patterns. If you have different people who do different transformations, different data analysis, they might have very different ways of doing these things. So you don't have the standardization that you get with the ETL process that's usually managed by the IT function. So that can be a drawback in the data lake as well. That being said, data lakes are a very useful tool to help us manage big data at scale and provide a structure that has much more flexibility than traditional data warehouses. And that's it for this part. In the last video, we'll talk about how these two types of paradigms actually live within an organizational context. Thank you.